to our presentation. We are the Macrosoft team. Our project is T-Nav. Our customer is Professor Starobinsky. My name is Nael Musleh. My teammates are Abin, AJ, Patrick, Raspante, Chen, and Ogorzalek. So I know most of you probably use the Beeline T. The objective of this project is basically to provide the Beeline passengers with accurate train arrival information for all the stations on the Beeline. The users will also have easy access to a website where they can check the arrival of the trains to those stations, and this will utilize the community of GPS-enabled cell phone users. The deliverables of this project are the cell phone application that will be with the user who's on the train, the server software, the server database structure, the user interface on the website where the user will go and check where the train is and also to plan a trip, and the user manual and design documentation. So the overview of this project is basically, there's a user on the train and he runs a T-Nav application. He makes communication with GPS satellites. It will send coordinates. It will get coordinates from the GPS receiver. It will send it through the internet to our server, and then our server will do all the calculations, algorithms, estimations, and we will be able to spit the train arrival times on our website when user interface. The requirements, I'm not going to talk about all of them. Basically, the most important ones are the HDOF has to be less than 100 feet for valid data. The packet size for the data sent from the phone to our server has to be maximum 70 bytes, 50 bytes for the data, 20 bytes for the UDP header. The time between each packet sent from the same phone has to be 5 seconds. And also there has to be provided confidence interval with error up to 1 minute from our motion model. Now I'm going to pass it to my teammate Chris to talk about the cell phone application.
Thank you, Nael. I was in charge of developing the cell phone application for T-Nav, which the user can take on the T, turn on when he's there, and will send all the data for the GPS phone to our server. The two platforms that we used was the Nokia E90 and the Motorola Abin 425. And so about the cell phone application, this is basically a Java to micro edition application, which is standard with all the Sun Microsoft general APIs for developing mobile applications for Java-based cell phones. The only constraint on the scalability of the system is the JSR 179 location API specification, which is supported by almost 80% of the phones currently on the market that have GPS chips that support Java currently. And there's also user notification possibility where the user can set interval time where the cell phone application will alert the user on whether it's running, so you don't forget to turn it off when you exit the T. And it's basically consists of 5 main modules in Java. The intro user interface, which provides the intro screen when the user starts the application. It allows you to set those notification options and start the actual application. Then we have the location module, which is a small Java class that uses the location API to call the server, the cell phone's GPS chip for location data and send that using the connection module through a UDP datagram, one-way communication straight to the server over the cell phone GPRS, 3G, whatever data network you're on. The user interface is a module that displays the information to the user while he's on the T. It'll show you some numbers with latitude, longitude, timestamp values, and whatnot. And the message UI, which allows the program to make static references to any alerts that might pop up to the user. And these are some screenshots of the cell phone application as used on the S60 Nokia platform. It looks the same on all phones that support Java and have that location API again. This is the user intro screen. These are some of the settings that are available to the user, and this is the way it works when it's actually running. And with that, I'll hand it over to Patrick to talk about our data acquisition and processing center.
The Data Processing and Acquisition Center, aka the Backseat, is our physical server down in the ECE Senior Lab. Its main purpose is to provide all the server software and algorithms from all the incoming data from the cell phones and produce the arrival times and predictions and provide them to the user interface on the website. Some of the technologies used were PHP for some of the database references, Java for most of the processes, Apache Tomcat for the web server stuff and the JSP, and MySQL for a lot of the database stuff. And right here is the DAPC breakdown and block diagram. Basically what happens is the cell phone will be sending data from our cloud of users, and from the internet will be coming datagram packets with latitude, longitude, timestamp, user IDs, and passwords. We have a small PHP script at the top that analyzes each packet. If the credentials are correct, it parses them and adds them to our two database tables at the top here. One called train data, which pretty much holds all the raw data, latitude, longitude, timestamp, stuff like that. And another table called users, which holds the current list of all the users in the system. Now, the bread and butter of the system, which actually manages all the trains in the system and creates all the predictions, is the motion model, which Chen will talk to you about in a second. Its inputs are from a file of station locations, and another process called segmenter breaks down the entire B line into discrete segments and feeds the segment array to the motion model. And the motion model also takes in current user locations along with prediction times, actual travel times between each station. And with all that information, creates delays and error predictions and provides them to the T-Nav website. Now, I talked about the train data table, which pretty much has all the raw data from the cell phones. And we figured, why get rid of all that data at the end of the day? We can definitely use the data to improve our estimates and predictions. So, the actual data in the train data table is pretty much a mishmash of data from all different users. So, one process, user processor, looks at this big mishmash of data and filters out all the different users in the system. It then finds all the associated data to that user. Then figures out which time of day the user took that ride, and provides all that filtering to station time 3, another process, which then looks at each user's ride and figures out how much time it took between each station. Then station time moves all that information to the relative prediction table, which I mentioned before, which contains the raw travel time between each station and puts it in the appropriate time of day table. For example, we might not want to lump all our data together because, between 6 a.m. and 10 a.m. maybe there's going to be a lot more traffic than maybe the middle of the day or even late at night. And I'm going to throw it over to Musleh. Chen, who's going to talk to you more about that motion model process.
So the motion model, as Pat says, is pretty much the main server-side software. Now, what it is it takes all the raw GPS data and turns it into something useful, puts it in the database so the UI can go ahead and look at that. So the first thing it does is it calls segmenter. What segmenter does is it takes the entire length of the B line and breaks it up into discrete segments. Now those points, those endpoints, are places where the train would naturally stop, like a red light or station. And once that initialization is done, we call active segment. It goes through all the segments and calls the users. And an active segment is defined as a segment that has users transmitting data from it. Now, once an active segment has been created, and all the active segments have been created, we go ahead and create a train. Now, this process is a little bit more complicated, and I'll explain that a little later. So once a train is created and all of the rules have been met, it goes into the motion model, which runs a very basic mathematical model to get the estimate for the train station. So we have all these segments, and they all have associated travel times, which are in the database and they're updated daily. And it goes ahead and sums those across from the train's current location, and sums across all the travel times and spits those out into the database. Now, the really important part of this is the train creation rules, because this is a way to prevent people from spoofing the system. So we have two levels of creation rules. The first one is on the user level, which creates a valid user. The second one is the train user rules. What you have first is the user must have 3 distinct GPS coordinates. That's going to be used later for getting the direction. But a distinct GPS coordinate means that the current coordinate and the one before it, the difference between them has to be greater than or equal to a threshold that we've created, which is about 2 train lengths. The next one is the user must traverse a segment at a predefined duration of time. We're sending data at about 5 set of data every 5 seconds. So in 15